Good morning all. Today we are going to do the experiment on basic refrigeration cycle for cooling. So where this cycle is used in mostly refrigeration applications like domestic refrigerator, air conditioning, freezer. So we have in equipment we have in the lab, and the name of the equipment is domestic refrigeration system. It it is made by Gunt ET415, working on R13A apparatus. This is a old deleted. So this is the equipment. So any basic system or any basic cycle consists of four process or four devices or four components. So say the domestic refrigeration also consists of four components. So one of the important component where we are desiring output, desired output. So like I want to cool the room, that is I want to cool the space, or I want to cool the water, or I want to make the food cool, keep the food cool. So this is a space, it is called a evaporator, where the desired output is taken. Then second part is a condenser. Then there is a compressor which is having inlet and outlet. There is a pressure gauge. We can measure the pressure at inlet and outlet. And the small part is number 3 is a expansion device, throttling valve. What is meant by throttling valve? I will explain in the working. So these four parts are combined together to form a cycle, and that cycle is called a refrigeration, vapor compression refrigeration cycle. So how it works? Now I'll explain the working. So how to do the experimentation? I will explain here. So there is a switch, on-off switch. So start the refrigeration system. Keep water bottle here, and after 10-20 minutes, come and take P1, P2. At regular time interval, you can record the P1 and P2. What is P1 is the suction pressure, and P2 is delivery pressure to compressor. So in the system, there is a low pressure and there is a high pressure at inlet and outlet of the compressor. So here, the condenser and compressor are at high pressure, so they are kept outside. That's why, and evaporator is at low pressure, so it is kept inside the room, and condenser compressor outside the room. Then it is called a split air conditioner to avoid the noise. The main function to avoid the noise. The compressor and condenser are kept outside in atmosphere, and evaporator is kept in a space or room. Now how it works? Now here I will explain the working. So I will start from the our desired output. What I want to make a water cold. I want to make a water fridge. I want to make a space cool. So this is a space. Keep the water bottle here. So through these tubes, a refrigerant R134. This is hydrofluorocarbon HFC. So this is a refrigerant 134 property table. We'll start the working now. So through these tubes, a refrigerant is flowing. So now here in refrigerator, the refrigerant is liquid. So initially consider it is liquid. Its boiling point and melting point is very, even it is in negative. So at the room temperature, or what is the water temperature? So heat will be absorbed from water to refrigerant, or refrigerant will absorb the heat from room or space or food or water, and it start boiling. It evaporate and forms a vapor. So outlet of the evaporator is completely vapor. So this outlet of the vapor goes through these tubes, the big tube. It will come through big tube, this white tube. It will come through this big tube, and it will go to the compressor as an inlet. So we can measure the pressure. P1, inlet pressure. Then its pressure, the vapor pressure is in temperature is increased to P2. This refrigerant coming out is a superheated refrigerant. So you can see here only vapors. It is invisible. So this vapors, superheated vapor goes to the condenser. So this is a condenser. So what is condenser? The name itself indicates steam condensed to water, like vapor condensed to fluid. So here the liquid is start condensing. Liquid is start losing the temperature. When it reach a saturation temperature, it will start converting liquid. So here you will get all liquid. Okay, so completely all liquid, only liquid. So this liquid pass through. This is a bigger area. So bigger area tube it pass through, and then the area is suddenly change. It becomes a small tube. So this tube is called a capillary tube. So part number 3 is capillary tube. Capillary tube, which acts as a throttling wall. Which acts as a throttling wall. Okay. So this part number 3 is a throttling tube, capillary tube, and it acts as a throttling wall. So what is the use of throttling wall? The pressure is dropped from bigger tube to smaller tube. This area is dropped, so pressure is dropped. So when pressure is dropped, the liquid pressure of the liquid refrigerant is dropped. Then some of the liquid is splashes. Then outlet of the throttling, you will get some vapor and some liquid. So it is a mixture. You will get a wet mixture. So this mixture goes to the evaporator. And in evaporator, this liquid will absorb the heat from the space. It will become dry saturated vapor, and this vapor again come to the compressor. So this is, and the cycle is repeated. That's why it is called simple vapor refrigeration cycle. Okay, so I will explain with the help of PV and TS diagram. Start from the evaporator. So this is a evaporator in which the tubes are inbuilt. This is the inlet and this is outlet. So this is a evaporator or space where the food or water is kept. So this is at a room temperature. So this refrigerator coming inside the evaporator is a mixture, vapor and liquid. Okay, super liquid. Now this liquid refrigerant, its boiling point and melting point is very low, even in -degree centigrade. So it will absorb the heat and it will start boiling. So here all refrigerant will become, the outlet of the evaporator is zero point 0.1, and it will be a dry vapor, dry saturated vapor. This vapor is compressed in a compressor, very high pressure and high temperature. So this is called superheated steam. This steam goes to condenser where there is a fan. So this fan will blow the air, and the refrigerator's temperature start from decreasing at a particular temperature, that is called saturation temperature. It start forming water, liquid. So the refrigerator coming out from the your condenser to atmosphere by rejecting heat to atmosphere will completely condense. That's why it is called condenser. So this complete liquid, high pressure liquid, its pressure is dropped in a throttling wall. So this is a throttling wall. The capillary tube is used in a household refrigerator. So this throttling wall will drop the pressure. So when pressure is dropped, so some liquid will flash. Some liquid will flash and it will form liquid vapor mixture. So here we are getting liquid vapor mixture. So here it is a liquid and vapor. Here it is completely dry vapor, here superheated vapor, and here completely liquid. L for liquid. Okay, so this question is very important. What is the state, what is the condition of refrigerant at outlet of each component? So this throttling means the pressure is dropped, keeping enthalpy constant, energy constant. So at point 3 and 4, enthalpy is constant. Okay, so this is the working of household refrigerator. Now with the help of block diagram, I will draw the pH diagram. pH, pressure versus enthalpy. On pressure versus enthalpy diagram, this is a saturation curve. And in TS diagram, this is a saturation curve. Okay, so it is different. It is little falling down and it is a little vertical. So this point is a critical point. Before the critical point, the refrigerant is liquid, and after this point, it is a vapor, dry saturated vapor. Same here, it is a liquid and dry saturated vapor. Now, first point I know the outlet of evaporator is at very low temperature and low pressure, and it is a completely dry vapor. So, dry vapor means on the curve. I know x is equal to 1, x is equal to 1 here, and here x is equal to 0 means it is liquid. So x is equal to 1 means on this, and this is a pressure, evaporator pressure. Then number 0.1 is here. Okay, so condition of vapor, the condition of refrigerant is a dry vapor. This dry vapor is compressed centripetally in a compressor to 0.2. So the condition of refrigerant is superheated. So this is a isentropic compression process. Isentropic means Q is equal to 0. So this superheated steam vapor enters in a condenser where the temperature is decreasing up to this point. So temperature lines are like this. So temperature is decreasing. At point 2 dash, it start condensing to liquid, and here 100% liquid, x is equal to 0. This point is called 4-3, outlet of condenser. Now, outlet of condenser is completely liquid, means it is on the curve. Then it will be expanded enthalpy, means enthalpy is constant, means vertical line to 0.4. Okay, so 4 to 1, 1 to 2, 2 to 3, and 3 to 4 is a cycle. Now on TS diagram, steam is compressed isentropically. See here, vertical means it is exactly straight line. So this is called isentropic expansion. Entropy is constant. Then point number 2. Then the heat is the vapor refrigerant goes to condenser. It start losing the heat at constant pressure up to 2 dash. Here it start condensing. Phase transformation take place at constant pressure and temperature. This is point number 3. It is on the curve because it is liquid. Then pressure is dropped in a throttling wall with a constant enthalpy. So this is a constant enthalpy. It is not vertical. The entropy may increase. And this is a constant pressure through the evaporator. Okay. So heat is rejected in a condenser. Heat is rejected in a condenser to atmosphere. Heat is supplied in a evaporator. Same here and same here. QR. Q, yes. And this is a W. I need to run the compressor, so this is WC. So there are four processes: 1 to 2 isentropic expansion, isentropic compression; 2 to 3 constant pressure heat rejection process; 3 to 4 isoenthalpic isoenthalpic expansion process; and then 4 to 1 constant pressure heat addition process. Now, what is our experiment? Now, 20-30 minutes, we will go to the apparatus and we will record the pressure. And the pressure is, here it is written 1 bar, not be 1 bar, it should be P atmospheric, P ATM, T1, and here it is P2, P ATM. So whatever I recorded, this P1 is a gauge pressure and P2 is gauge pressure. Now the gauge pressure recorded is 1 bar, plus atmospheric pressure is 1 bar equal to 2 bar, and the compressor discharge pressure recorded is 9 bar plus atmospheric pressure 1 bar equal to 10 bar. From property table, how to get T1. So there are two T2s. One T2 is a saturation temperature and it is shown by 2 dash. I will show on the PV diagram. And there is another temperature T2, that is, this temperature is a superheated temperature because second condition is superheated steam. So we need to record that, so I added there. Okay, so how to calculate that and how to calculate these values, now I will explain from table. So let us start. So at state 1, that is, I told you it is the point 1 is on curve. So what is the meaning of curve? Where x is equal to 1, the refrigerant is a dry saturated vapor. So at point 1. So what I recorded from P1, this is a gauge pressure. P1 is a gauge pressure. So it is a 1 bar. So 1 bar. So I need to calculate a absolute pressure for P1. Simply, no need to write absolute. But if it is a gauge, you need to mention. So absolute is equal to P1 is equal to P gauge plus P atmospheric. It will give me 1 plus 1 is equal to 2 bar. 2 bar, 2 into 10 to the power 5 Pascal. So remove 3 kilopascal and 2 zeros on 20 kilopascal. Okay. So P2 is equal to directly P2 gauge is equal to 9 bar. So I will calculate P2 absolute is equal to 9 plus 1 is equal to 10 bar, and 10 bar is equal to 1000 or 1000 kilopascal. So as I know the pressure, this is P1 pressure on pH diagram. So this is P1 2 bar and P2, this pressure is 10 bar. Go to the table, saturation table, and find out. So 2 point is here, 2 dash. So point 1, 2 dash, 3 are on the saturation curve. So I will get the properties at that point from saturation table. So this point 4 is a mixture. I need to find by formulas. Point 2 is a superheated vapor. I need to find by some property table. So we can solve this problem by 3 methods: by property table, number 2 by chart, by pH chart, and by test software. So I will explain the property table by property table, and which will be similar to the test software. So you can try by using test software. I will not explain. So for test software, refer my previous video. pH chart I will explain. Now first a property table. From property table. At state 1. What you know at state 1? The point 1 is on saturation curve. means it is a dry saturated vapor, means X is equal to 1 and pressure is equal to 2. So as I told you, we need two properties. So P1 is equal to 200 kilopascal and X1 is equal to 1. Means it is a dry saturated dry vapor. So go to the steam table and find out the all properties. HFC hydrofluorocarbon 1234A. Go to the saturation table. Yes, this is a saturation property table on temperature basis. I don't have temperature, I have pressure. Or from gauge, I can record the temperature also and I can find it. I have the pressure. What is the pressure? 100 kPa. So here see kPa absolute. Go to the property table at 200 kPa. Yes, this is exact 200. So I need to record. Now currently I need Hg and Sg and temperature. And here 392, 392, and this I need to record. So I will write here H1 is equal to 392.9, S1 is equal to T1 is equal to minus 10 degrees centigrade, 1.7341. So write unit kilojoules per kilogram, kilojoules per kilogram, Kelvin, and degree centigrade. At P1, I need HFG also. Okay, so I can write. So no need to come back again here. So this is Hg, this is HFG, this is H1. So I write Hg, HF. HF1 means this point HF1, and this is Hg1, that is equal to H1. So this is Hg1, H1, because dry saturated HF1, HFG1. So I will record this also. 186.7, 186.7 and 206.2 kilojoules per kg Kelvin. So first I will find all enthalpies and what I know at state 2. Yeah, it is a superheated. I know the pressure only and entropy is constant because it is isentropic process. So S2 is equal to S1. 2 is equal to 1000 kilopascal and S2 is equal to S1 is equal to 1.7341 superheated vapor. So go to the superheated vapor at 1000 kilopascal and S is equal to 1.7341. Find out the enthalpy. Hg is nothing but H2 dash, and then Tg, that is equal to T2 dash, then T2, then H2, T2. Now go to the steam property table. See the page next. It is again dry saturated. Yeah, this is saturated property table. Next page. Superheated vapor. Pressure is 20 bar kilopascal. So go to the 1000. 1, 2, 3, yeah, 100, 170, 200, 250, 900 kPa, and now here 1000 kPa. Now entropy is 1.73 I found here. So what is the temperature? So record this property. I need a enthalpy, I need entropy, no need. Specific heat I need, volume I don't need, temperature I need. So enthalpy is 425.7, 425.7. T2 is 45. And the saturation temperature at this line, it is a saturation temperature. Temperature is 39.55. Saturated liquid and saturation vapor, the temperature remains same. Okay, only enthalpy. So Hg, because it is a vapor, so I need Hg is 419.5. So temperature Tg or Tg2 dash is 30, and Hg H2 dash is equal to 419.5, 419.5 kilojoules per kg Kelvin. Now it is asked in the report. It is asked in the report, find out H2 by this formula. Find, yeah, this is format. So H2 by this formula at P2. So I need a superheat also, specific heat. I need a specific heat. So specific heat of the superheated steam is from the table. So what is the 45 degrees centigrade is the temperature there. So you can use this 1.0928, 1.0928 kilojoules per kilogram Kelvin. So this is a specific heat I need. Now I can calculate H2 by this formula. H2 is equal to H2 is equal to H2 dash H2 dash plus Cp T2 minus T2 dash. See, H2 is equal to H2 is 4919.5 plus Cp is 1.0928 into 45 minus 39 point. I will get H2 is equal to 425.67 kilojoules per kilogram. And here what I wrote. So this value 425.7, and by calculation this value is C. Both values are correct. So no need to find this. I'll by this formula. Yes. Already we got from the steam table. So why to find? So state 3. So what I know at state 3, P2 is equal to P3 is equal to P3 is equal to P2 is equal to 100 kilopascal. And what is the another no? This point is on saturation curve. Means x3 is equal to 0 here, and here x is equal to 1. X3 is equal to 0, saturated liquid. Okay, so H3 is equal to HF3 is equal to, at point 2, if I write HF here, this is HF here, 255.6, 255.6. So same here. Or go to the saturated liquid. So this is a saturated liquid at 1000 kPa, HF, right, HF, same. I will show you again here, 255.6. Now this is a superheater table, saturation table, and go to the 1000 kPa. In between these two columns, where is HF? Yes, I think, yeah, this here. 255 and 256.6. So I can get the average of these two, because so I can use this interpolation here. Okay, so I need to find interpolation. So what is the value in between this? So I have the temperature here. So Sg and Sf. This is Hg, Hfg, and Hf, and this is temperature. Okay, so how to use interpolation? Now column, and I need a temperature. Temperature already I calculated 39.35. I got from superheated temperature. It is here. Okay, so no need here. You can go to the superheated. No need interpolation. Control Z. See, you need to use the logic. The 2 point, the pressure 1000 kPa. 1000 kPa is here, but I found in superheated table. I have HF here. I have temperature. So why to use interpolation? Sorry, HF is here directly. Okay. So this is a saturated liquid, and this is a HF, and these properties are on saturation. So 255.6. So H3 255.6, and the temperature is already I wrote here 39.5. 255.6 I wrote here. Okay, so point 3 is done. Now point 4, state 4. So P4 equal to P1 equal to 200 kPa. So already I wrote at 200 kPa all the properties, I wrote it here. So H3 is equal to H4 256 kilojoules per kg. But it is asked find out X4. How I can find X4? Okay, otherwise I can stop here, but it is asked in the problem. So my target is to find out all enthalpies. Okay, I finish all enthalpies. But meanwhile, here also it is asked find out H2 by calculation. Find out X. What is the condition of refrigerant coming out from throttling wall? What is the condition of refrigerant coming out from this point? What is the X4 here? Here, see, as I told you before, after throttling, the refrigerant will be fast and it will form mixture of liquid and vapor. Here it is liquid, here it is vapor, here it is a mixture. Okay, so now I need to find X4. So how will find X4? Now H4 is equal to, how I calculated H4? At pressure 200 kPa, if you see here, at pressure 200 kPa and 200 kPa, I need to find HF and HFG, and we need to find HF4 in between. So HF plus X HFG. This is, I have already here values. So 256.6, 255.6 is equal to HF is 186.7 plus X I don't know, multiply by HFG is 206.2. So I will get X is equal to, that is nothing but X4. I will add the 4 here, 4 here, add 4 here, because at pressure P4 equal to P1. So X4 is equal to 256 minus 186 divided by 206, 0.3341. So 33% liquid and 67% vapor. From property table, I calculated H1, H2, H3, H4. Similarly, I will calculate it from the pH chart. So I can write H1, H2, H3, and H4. Okay, now pH chart. Here is 2 bar here and 10 bar here. Okay, I need to draw horizontal line at constant pressure. I need to draw a constant pressure horizontal line. At 10 bar, you will get 40 degree centigrade temperature. See, so 40, 40 here, 40. This line is correct. So I need to keep on this. I need to keep on this bracket. See, here is a bracket and here is a bracket. Okay, so these are the temperature lines. See, 70 degree here, like this. Control Z. So 70 degree temperature is here. It is a constant. Then temperature goes line up. The temperature goes up, and here it will come down. So this is a temperature line here, like this. Okay. So this, now I will draw the another pressure line. This is a P1, P2. Now I will draw a P1. So P1 is 2 bar. So 2 bar is here, and temperature is minus. Temperature is minus 10 degree here, say. So it should pass through this. Yes, correct. And it should pass through this line, and it will touch to the saturation curve. Correct. Okay. So this is P1. The temperature here minus 10 degree and my 40 here. See, I wrote from the table and chart. So values are same. Now, isentropic compression. Isentropic compression is from this point where it touch on this curve. I need to go parallel to this. See, these are the isentropic lines. S is equal to 1, S is equal to. These are the isentropic lines. I need to go from this point isentropically like this. So I will draw the line parallel. I will draw the line here. See, along this line. See, it is correct. Now I will move this line up to that intersection. Yes, this is more correct. Little see this gap. This gap and this gap is decreasing. Means little I am yes here. And see the temperature is 45 near about in between 50 and 40. See here temperature is 45. So what I wrote here 45 from table. And now from chart same. From chart the T2 is 6.2 where temperature is T2 is equal to 45 degrees centigrade. Now this point is 2 dash, 2 dash where temperature is 40. Now at constant pressure heat is rejected and it will touch to here the saturation curve and this point is 3 where it becomes liquid. And then the vapor, this liquid is expanded isenthalpically means vertical line H is equal to constant. H is equal to constant. So I will draw the vertical line. I got the point. Now I got the point number 4 where enthalpy is constant. So H3 is equal to H4. So I got this. And now this is point 1. So this is pH diagram. Find out the enthalpy from this. So how we find the enthalpy? So this is my vertical line. Take your ruler and put the ruler and move ruler like this. At 2, stop at 2. And what is the enthalpy? 430. So it is less 428. So yes chart, I will write here H2 is equal to H2 is equal to 428, 26, 25. By table it is 25. I will write 26. It doesn't matter. Okay. Now again move this line to point 1. H1 is equal to 390, 234 up to you. Okay. Then I will again move this line to H3, H4, which is 3 is equal to H4 is equal to 256. Okay. So we have all the values. Khalas, chart method finish. Now in test software, so you transfer this value in your table here. Okay. Now pressure also you can write here. And now we will do the performance analysis. What is performance analysis is this. So I will explain first here in the diagram. So during process 421, the heat is added. The heat is added QS, and this is called a refrigeration effect. So refrigeration effect or heat added in the system H1 minus H4. 1 to 2, we need to run the compressor WC, work required to run the compressor WC coming inside, and then the heat is rejected in the atmosphere QS in condenser. So if you apply the first law of thermodynamics, what is in here? QS plus WC. is equal to QR. So WC is equal to QR minus QS. Now specific heat absorbed by the evaporator called as a refrigeration effect, and it is also QS is equal to H1 minus H4, and it is expressed as, so we have the H1, we have the H2, H4, so you can use the values from chart or you can use the values from here. Okay, so H1 minus H4, so H1 is this and H2 is H4 is 256, so 392.9 minus 255.6, so you'll get that. Number 2, heat rejected to atmosphere in condenser. So where is condenser? QR is equal to between 2 and 3, so H2 minus H3. So H2 is 425.7 minus H3 5.6. Okay, so we'll write the answer here. Heat rejected. So our first aim is to find out QS, QR, then W. Work required by compressor. Compressor is equal to WC. So here you can do the subtraction of these two or directly from chart where is compressor 2 to 1. H2 minus H1. So H2 is 425.7 minus H1 is 392.9. So really, machine means efficiency, but efficiency word is not used for refrigerator. It is not giving any useful what it is a useful, but it is for comfort or but it is damaging the environment. So the efficiency word is not used for the refrigerator exchanger because they are exchanging only. What is the use? Exchange only, like an agent. Another terminology used is called coefficient of performance is equal to COP is equal to it is like efficiency, output by input. So what is the output from this system? What is the output? I want this is a desired output. It is not called output. It is a desired effect. What I want to absorb the heat from food. I want to absorb I want to cool the water. I want to cool the space. So this is a desired effect, H1 minus H4 QS. So this is the output. It is called desired output and it is QS. And what is the input? The compressor work, electricity. So the formula is the evaporator is H1 minus H4 and compressor is H2 minus H1. So we have this value already. So 170.1 and this is write the unit kilojoules per kg, kilojoules per kilogram, and this is 33.8. Okay, so I have the values and I will plot it here. H1 already directly QS. Where is QS? QS is this 137.3 and WC is 33.8. So COP of refrigeration is equal to 4.062. It has no unit. Okay. Number 5. COP of heat pump. It is asked. So what is heat pump? It is a reverse vapor cycle. Heat pump means I want to now here I want to cool the room. Now in summer, in winter, I want to heat the room. So the cycle is reversed. Cycle is reversed, and the refrigerator will act as a heat pump. And nowadays, if you have the air conditioning, heating and cooling both. Okay, so there is adjustment for reversing the cycle. So here the desired output is QR and input is WC. So cup of heat pump is R by WC. Okay, so what R is equal to QR minus QS. This is nothing but 1 plus cup of refrigeration. How? Now I will show you this formula. See here. I will consider this 1 plus what is cup of refrigeration? QS by QR minus QS. Okay, so I will take the LCM. QR minus QS. So this will go here. QR minus QS plus QS. So QS get cancelled. What is remaining? QR by QR minus QS. So there are two formulas, two ways. So you can use any one and your answer will be correct. So here I can write 1 plus 4.062 or 5.03. Same answer you will get. So both answer will be same. So it doesn't matter, but better to use this formula. This is very important. So keep this. It will show you the some calculation. So no problem. This is cup of heat pump. Now there is explain what is Carnot cycle. Have you studied? It is in theory. Okay, you study in theory. So I will explain how it is work Carnot cycle. Okay, it is not so important, but I will explain what is meant by Carnot cycle. So this is a source, and this is a engine, Carnot engine, and this is source and sink, which is working on T1 and T2. So if heat is flowing, so this is a refrigeration cooling cycle. Okay, so cooling means we need to supply the work, and this is supplied and this is Q rejected. Okay, so I want to make this temperature T1 very cold, so T2 is greater than T1. So this is called a Carnot cooling cycle. Okay, I want to make temperature cool, I need to pump this. So what is the formula for this? So cup of Carnot cycle for cooling, it is written. What is the desired output? QS by W. What is W? QS by QS minus QR. Sorry, QR minus QS. No, it doesn't matter. QR minus QS. Okay, so QS is taking place at temperature T1 and QR is taking place at temperature T2. T2 minus T1 in temperature. So Carnot cycle is a hypothetical cycle which doesn't depend on mass and there is no working fluid. So it is a hypothetical cycle. Okay, so Carnot for cooling and for so find out cup of Carnot for cooling is equal to T1 is now here. What is T1? Go back up. So from chart I wrote T1 is minus 10 degrees centigrade. So T1 is minus 10 degrees centigrade and T2 saturated. T2 saturated is 39.35. Okay, so this is 39.35 and this is minus 10. Now this is called T1 is equal to T4 and this is T2 dash. Okay, so here I will use that now. So it is very important all this temperature should be in Kelvin. In lab manual the formula is written as 273. Why 273? Because temperature T1 is degree centigrade and here if you put Kelvin or degree doesn't matter. Okay, but here if you put Kelvin, if I sum up the table the temperature is given in Kelvin, so your answer will be wrong by this formula. Okay, So don't use this. This is a basic formula. Okay. So where temperature should be in Kelvin, should be in Kelvin, Kelvin. So minus 10 plus 273, and here minus 99.35 plus 273 minus minus 10 plus 273. So write your answer. This is a cup of Carnot cycle. This 273 and this 273 will get cancelled by this minus. Okay, so your answer will be, and cup of heat pump, cup of heating, Carnot heating, Carnot. So desired effect is heat rejected, QR minus QS, WC. Okay, so heat rejected is at T2 and T2 minus T1. So in minus, it doesn't matter if it is degree or Kelvin, 10.64. Sorry, this is a mistake here. That is wrong. So I will calculate again. 5.32, 5.32, 5.329. So this is cup of Carnot cycle and this. So we finish this all calculations. We find out dash. Now draw the pH diagram. Write this solution procedure. Complete this chart. Complete this table as I explained, and write the conclusion. Thanks. So this I will show you in the Zoom view. Thank you very much.